Just realized that. I'm going to first share my screen. Oh, I need to be given permission to share my screen.
Give me a moment.
Okay.
Okay, good. You should have been a co-host already, but my fault. Now you are.
Okay. So we're going to start with these slides and then we'll move over to the model. So I'm going to be sharing with you the En-ROADS model. En-ROADS stands for Energy, Rapid Overview and Decision Support Model. This is a model that was developed by an organization called Climate Interactive in collaboration with MIT's Sustainability Initiative. And it's a systems dynamics model. And so what that is instead of looking at each individual solution, you can look at them individually, but know that as the Earth system and the social system and the economic systems all interact with each other, as you add different solutions, they're not linearly additive in terms of their impact. And so this model helps you see what the collective impact is of a group of solutions are. So we're going to start with a brief introduction here, and then we're going to explore scenarios of success. I will show you how the model works, and then I will share the link with you, and then I will ask you to suggest, with you being able to test out, try things out in the model yourself, you'll be able to suggest other solutions, and we will be trying to get to a goal of keeping global temperatures from rising no more than 2 degrees Celsius by the year 2100. And then we'll have a brief debrief. So let's just briefly review the science and what's at stake. This is a graph of the carbon dioxide concentration in the atmosphere. And this, let's get oriented. This is the present here, and the present in this graph is defined as the year 1950. And time does go from left to right, but here we have the present here, and we go back 800,000 years before 1950. And then the vertical scale is the carbon dioxide concentration in parts per million. And so that goes from 160 to 480 parts per million. And if you've been sort of hearing about the levels of carbon dioxide, here's the current level is it's close to 420 parts per million now. But it didn't really exceed 300 parts per million until about 1950. If you look back in the geologic record, you can see that about 675,000 years ago was about 170 parts per million. There's been quite a lot of variability over time, and about 325,000 years ago, it was about just almost 300 parts per million, but it's varied within those ranges. So where did all of this extra carbon dioxide that's represented here by this near vertical line come from? So here is another graph that shows the different sources of carbon dioxide emissions. The graph goes from 1850 to 2018, so a very different scale from what we just looked at. And this is the carbon dioxide emissions in gigatons of carbon dioxide per year. And you can see here that in 1850, most of the emissions of carbon dioxide into the atmosphere were land use changes. This is the clearing of land from forests to fields for agriculture is mostly what was happening at this time. But you can see in the late 1800s, coal became starting to become a significant part of society's energy use. And that has grown over time up until recently. It's gone down a little bit. In the early 1900s, oil became a significant source of energy and has grown over time. And then in about 1950, natural gas also added the mix of energy sources and thus emissions of carbon dioxide into the atmosphere. These other gases here, which is a small red wedge starting in about 1950, were emissions from cement production and gas flaring. What we mean by gas flaring is that in the production of oil, a lot of times there is a byproduct of methane gas. And you can either release that into the atmosphere, which is another greenhouse gas, or you can burn it. And that's what the flaring is. Of course, that then puts more carbon dioxide into the atmosphere. And then there's the land use changes, which have gone up and down a bit over time, but have not really changed dramatically. This is carbon dioxide is only one of a number of greenhouse gases. This graph, again, goes to the same time frame on the horizontal axis, 1850 to about the present. The greenhouse gas emissions, instead of gigatons of carbon dioxide per year, it's carbon dioxide equivalents. So methane, for example, is a much more, per molecule, is a much more powerful greenhouse gas than carbon dioxide is. But there's much, much less of it in the atmosphere. And so what they've created, in order to make this graph, they've put an equivalence of this much methane is the equivalent of 18% of all of the greenhouse gas emissions in terms of its power compared to carbon dioxide. So you can see here that from the previous graph, the carbon dioxide from fossil fuels is about 68% of the total emissions of greenhouse gases. 7% came from land use and forestry. Methane, which a lot of that has come from agriculture and from industrial productions. This is the methane, is 18%. And nitrous oxide, which also comes from agriculture and industry productions, is 5%. And then there's the F gases, or fluorocarbon gases. These are man-made gases developed in the 1950s that are used for refrigerants. And at the time that they were developed, at sea level pressure and temperatures, they were basically inert. But they've got released into the atmosphere and have caused other kinds of problems, like the Antarctic ozone hole, which is an impact on the Earth system, but not a climate change impact. But they are also, per molecule, a very powerful greenhouse gas. And so that's included here also. So what is this impact of all of these greenhouse gases had on global temperature change from pre-industrial times? Well, we have two records here. Again, this scale is from 1850 to approximately the present. These are temperature anomalies, which means that it's a change in the temperature from some set time. And in this particular case, that set time is 1850. So you can see that the temperature anomaly for 1850 is 0. There's two records here. This one, the red, is from the Hadley Center for Meteorology in the UK. And the orange line is the Goddard Institute for Space Studies here in the United States. And you can see that pretty much the records are made up of different observations. And so there's some variability, but they pretty much are very similar and all the way through up until about 1970. In 1970, we began to have the satellite records. And since then, these records are completely in lockstep with each other, with an increase since 1850 of about 1 degree Celsius or 1.8 degrees Fahrenheit. So this is a screenshot of the model we're going to be using, and it shows you the what is predicted. If the baseline scenario is basically if the world continues on the path that it is currently, the temperatures will increase by 3.6 degrees Celsius or 6.5 degrees Fahrenheit by the year 2100. This scale now was shifting from before in the year 2000 to 2100. The Paris Agreement set goals of 2 degrees Celsius with striving for no more than 1.5 degrees Celsius, and that's what these red dotted lines here are. And so right now you see the black line, which is that baseline scenario I talked about, and the current scenario where right now we haven't implemented any solution, so it's the same as the baseline, are the same here. But this is what we're going to be looking at. But even a 3.6 degree Celsius increase in temperature can have really serious impacts on the climate system. So these are just some examples of what that much warming would mean. The Arctic sea ice could be gone 2 out of every 3 summers. In recorded history and even in geologic history, the Antarctic sea ice has never been completely gone. It has decreased a lot. So the Arctic is now the minimum we have seen in September has been on the order of 2/3 of the entire Arctic Ocean. But it's predicted that that could be gone 2 out of every 3 summers, which has a lot of implications for the amount of solar radiation that's absorbed by the Earth system. In addition, insects insects could lose about 50% of insect species could lose over 50% of their habitat. This has tremendous implications for agriculture as we depend on insects to pollinate the crops that we grow. Drought could be 11 months longer than it is on average now. And burn areas, and we've heard a lot about the burn areas in the western part of the United States and in Australia. It's predicted that summer wildfires in the Mediterranean would double compared to today. Another area that's impacted, another feature that's impacted is sea level. Sea level is rising. And so this is the New Orleans Gulf Coast today. And so you can see here's Houston, Texas, and New Orleans over here, with a increase of 4 degrees Celsius. All of this area would be completely underwater. So you would lose New Orleans completely, and a lot of the Gulf Coast would disappear underwater. This is Manhattan today. And I'll just make a note here to pay attention to this part of Manhattan. This is where Wall Street is, the southern tip of Manhattan. This is the New Jersey shore over here. This is Brooklyn and Queens over here. With a 3.5 degree increase in temperature, all of the southern tip of Manhattan would be underwater, and pieces of it would be smaller islands. The Jersey Shore would be completely underwater, and a significant amount of Brooklyn and Queens would be underwater. So the reason I'm pointing out this southern part of Manhattan where Wall Street is this next picture is of Wall Street today. This is the bull on Wall Street. We are getting more people back. I'll call your attention to these two women walking by this window. Their heads are about the level of about halfway up the window. With an increase of 4 degrees Celsius warming, you can see that the water level will have risen to 3/4 of the way up that window, and so all of Wall Street would be underwater. So that's Manhattan, but here is London. Here is Parliament in London and the Thames River. And you can see that the entire first floor of Parliament is underwater, and the ends of the Westminster Bridge are completely underwater. And this is another part of the world. This is Shanghai with 4 degrees of warming. You can see all of the downtown area is underwater. So climate-related disasters have cost the world $650 billion just between 2016 and 18. But the IPCC has estimated that damages associated with global warming could total over $54 trillion by the year 2040. So there really is an urgency about addressing this issue. So we're going to be using this model, and I'm going to orient you to the model and then share the link to the model so that you can help me and we can collectively work towards keeping the temperature increase to no more than 2 degrees C. So here are the panels we're going to be looking at. These are the global sources of primary energy. And I'll review those a little bit more detail when we get to the live model, but you'll see that these are all the sources of energy: coal, oil, gas, renewable energy, bioenergy, nuclear, and new zero. What this new zero carbon is imagining a new technology that is invented that is cheap, that produces cheap energy with no carbon emissions, no greenhouse gas emissions. So that's what this one is. And so we're going to be looking at all of these different sliders here. Now, there's two things I have on this slide, and the slides are shared in the Google Doc. The link on this slide gives you access to the dashboard and the multi-solving tools. Those are also in the Google folder that I've provided you. This is just a different folder, but I'm just going to review that a bit. So let's pay attention first to these three columns here. This is energy supply, so that you can impact solutions for coal, oil, natural gas, bioenergy, renewable energy, nuclear, new zero carbon, and you could implement a carbon price. We have transportation and buildings and industry, both you could increase the energy efficiency of both of those, or electrify both of those. And then there's growth, both population growth and economic growth. And we have land and in industry emissions. There's methane and others. So this is the non-carbon dioxide greenhouse gases. And then you can impact deforestation, reducing deforestation and promoting afforestation. This is a carbon removal solution. So afforestation is one of them, and then technological carbon removals. So those are the different solutions we can implement. And if you go to the Google folder, you will see this document here, and it just gives you an idea of how you would relate to what pulling these different sliders mean. So for example, coal would be you're discouraging or encouraging the mining of coal and the burning of it in power plants. Or if you're down here with population growth, you assume a higher or lower population growth. New zero carbon, as I mentioned, discover a brand new cheap source of electricity that does not emit greenhouse gases. Or the technological carbon removal, pulling carbon dioxide out of the air with new technologies that enhance natural removals. So I want you to start to think about, in addition to this, and this is where you can bring to your students the social aspects of climate change and not just the science aspects of climate change. A lot of the solutions that we're going to be exploring take a long time to actually have an impact, but there are near-term co-benefits for society from the proposals. Think about what those might be, and we'll explore some of those also. And then also, how do you ensure that vulnerable communities are not disproportionately affected by your actions? If you put a high carbon tax on, then that may make energy unaffordable by a lot of communities. So think about those aspects also. So I want you to think about what kinds of actions you can help that you might take to mitigate climate change, thinking about these solutions. And we're now going, this is the live model. And as I mentioned before, this is the global sources of primary energy. I did change the graph because I prefer the lines, but there's lots of options here. You can change back to that area graph. I prefer this, and you'll see why in a minute. I've changed this graph to temperature change so that you can see really the impact of when our solutions actually have an impact. And here are the various kinds of solutions. And so if on the live graphs, you can scroll over and you can see, for this example, oil is a red line. And by 2058, it's projected that the energy from oil will be 262.53 exajoules per year. So this is the vertical scale here is exajoules per year. It's an amount of energy per year. And the scales on all of these graphs are the same now, 2000 to the year 2100. So I'm going to ask you now to think to suggest which of these solutions would we like to implement now. Which ones would we like to try? And I want you to put that into the chat. And I'm going to see if I can find the chat. Chat. Okay, here. Oh, so okay. So people have. Okay, less oil, afforestation, less oil. Okay, so we're going to try. We'll try first less oil. And so one of the things you can do with less oil is you can tax it. So if I move this here, and what you can do, and this is very powerful because there's a lot of things happening at one time. You see that the temperature changed here, the line changed here, lines changed here. There's a little tool up here in the upper right-hand corner. It says replay last change. So you can click that, and it shows you, it goes through a couple of times what actually got impacted. And you'll notice here that coal is impacted the most because you're taxing coal, but notice that there are other impacts. And what are the other impacts? The most noticeable ones are that oil, natural gas, and renewable energy go up slightly. And that's because you're taxing coal, but you're not taxing oil or natural gas. So people shift from using coal to using oil and natural gas. And then there's also the people shift to using renewable energy. So that's one. And then somebody suggested afforestation. So I'm going to implement afforestation here. And you see, it got down, we went from 3.6 to 3.5 with the taxing of coal, and then down to 3.4 Celsius with increasing afforestation. And so we can replay that too. and see how that impacts things. And you'll see that the temperature changed, but because afforestation doesn't impact energy, primary sources of energy, this graph on the left doesn't change at all. Okay, are there other suggestions? There might be. I just can't see them. It's population growth seems to be a major driver. Increase energy efficiency. Okay, let's try a couple of those. Population growth, we're going to slow population growth. And what that means is there's less demand for energy out in the year 2100. So you're not making population go down, you're just slowing the growth of population. If I replay that, it didn't have a huge impact on the temperature. But you can see that almost everything else went down a little bit. Oil, renewables, natural gas, coal. The others were impacted much less, as bioenergy and nuclear energy. Okay, so now, and there was another, energy efficiency. So for energy efficiency, I'm going to show you another feature here. And I'm going to assume you didn't say which energy efficiency, buildings and industry or transportation. So right now, I'm just going to do transportation. And we're going to, so next on the right-hand side of each of these solutions are these 3 dots. And so what we've been doing is we've been implementing solutions at a very high level. And if you have middle school students, everything can be done at this level, and you can get across to your students the complexity of the situation and how it really impacts a lot of different communities, different aspects of the Earth system and society. But if you click these 3 dots, it gives you extra ability to change things. So the status quo for energy efficiency is that you're increasing the energy efficiency of transportation by 0.5% per year. So you can change that, and I can change that to 1% per year. And you can see it has a very small change, and it doesn't actually, the energy intensity for the GDP is really, it diverts from the baseline by the slightest of margins. If you watch this, if I replay it, you can see it move very slowly. And you can change the year that it starts. The other aspect that provides you more information for you and your students is that this little eye over here provides you with examples of implementing this solution, like dynamics of what the solution means. But one of the things that I encourage people to look at are these potential co-benefits of encouraging energy efficiency. So improved air quality is a result of burning less fossil fuels. Better fuel efficiency means energy costs are lower, and so on. Equity considerations in some developed countries, such as the United States, pedestrian and cycle-friendly infrastructure is concentrated in wealthy communities. So others, low-income families pretty much get left out of that. So you can consider those things. And then in considering that improved air quality, let's go to one of these impact maps. So there's lots of different graphs here. Here's the impacts. So we've been looking at temperature change. We're going to go to air pollution from energy. And you can see while the impacts on the temperatures have not been all that great, we've only gotten from 3.6 degrees increase by 2100 to 3.3, you can see almost an immediate impact on air quality. So these is one of those co-benefits that's beneficial to society. And so it's worth the cost of implementing. Other graphs, we'll get to other graphs in a minute. So I want to show you one other one. We're going to go over here and look, basically I'll call it under the hood for coal. So the very highly taxed coal is set here at $47 per ton. And you can set the year that the subsidy starts or the year that the subsidy stops. You can also say reduction in coal utilization. And what that means, if somebody says one of their solutions is to use less plastic bottles, well, oil and coal are the energy source for creating those things, so that you can just set it in a percentage increase, a decrease of coal utilization. So if I say 25% here, you can see that, well, there's a impact on the air pollution, but also on coal as a primary energy demand. And you look at that, I think that is reflecting of this brown line here. The other one that you can change is stopping to build new coal infrastructure. This means is that coal companies have very expensive plants and they have a 30-year lifetime. And so if these plants, even if you implement zero carbon sources of energy, these plants are still going to be going until they run out of, until they have to be retired. And so you can in here, you can accelerate plant retirement. You can have different ways of, but you can also stop the building new coal infrastructure. And you can see the tremendous impact that that has. Okay, so what I'm going to do now, so we don't have a tremendous amount of time left, is one of the other things you can do is I'm going to start now from 0. You can set this back to being the 3.6, and you can share the scenario. I can copy this link, and I'm going to put this link in the chat. And I'm going to give everybody 5 minutes. I'm going to find the chat first. A lot of times I do this in breakout groups, but we really don't have the time to do that now. So here's the link to the model. And I want you to go in and I want you to try to identify, put in various solutions and look at what you find as the highest leverage solutions. Some are more impactful than others, but don't look at them one after another in terms of adding them together. We're going to add them together when we come back to when we come back together, and people can offer their solutions. But try out things like maybe subsidize renewables, see what impact that has, and then put that back to the status quo and play with the energy efficiency or electrification of transport. And then put that back and see which ones you think are the highest leverage ones. And I'm going to give you about 5 minutes, and then we'll come back and I'll have everybody offer what solutions, and we're going to build. What we're going to try to do is to get this, let me go back to here. We're going to try to get this temperature range to come down to this dotted line of 2 degrees C collectively. Okay, so we have 5 minutes from now. So it's 3:53 Eastern time. So 4:03. Okay. If you have any questions along the way, you can put them in the chat. Okay, so while you're playing with it, so somebody asked, how do you change from the tab air pollution to energy, to the energy tab? So I'm going to demonstrate that here. Here's the different graphs. Some of them change the graphs on the left, but if you want to change the air pollution, if you want to change it back to energy, you go to the graphs and the primary energy demand totals, and then global sources of primary energy. The one on the left, the other way to do this is there's a grid up here on the upper part. If you click you can choose, this is a sort of a shortcut to get to various graphs. So there is the air temperature one here. There's sea level rise, greenhouse gas emissions. These are all in that menu I'd also. Did that answer your question, Orkan? Also, I added wrong. So we'll go till 4 o'clock. I added 10 minutes instead of 5 minutes. We'll go to 4 o'clock.
Tamara, you can have until 4:15 for your session.
Oh, okay.
We'll still be okay because
All
we
right.
were running a little late earlier.
Okay, great. So I don't think any one solution is going to get you to 2.0. I don't want you to, right now, I want you to find what's the highest leverage solution, not trying to by yourself to get to 2.0. Okay, so when one person said that, Laurie, you said to jack up the price of carbon. If you jack up the price of carbon, just think about what else you need to do, because if you jack up the price of carbon, you make energy very expensive. And there are graphs here which we can explore on the cost of energy. So if I jack up the price of carbon, you can see how much that increases the cost of energy. But it is a high leverage one. That's true. And we can explore that when we come back to collectively start adding these together. Looks like changes to building and industry are really important. So we'll, yes, absolutely. Which one did you look at? Energy efficiency or electrification of buildings and industry? You did both. Great. Which one had a bigger impact? Methane in agriculture. That's also a very interesting one to explore. Okay, we'll give you 1 more minute and then we're going to start actually implementing. I think what might be most effective if we have people start talking. I'm going to ask you, can people raise their hands and I can call on people to offer solutions?
They can, folks, if you want to raise your hand, you've probably been doing this before. You go to reactions and pick up one.
Oh, I know. I think it's better if they go into participants and raise their hand there, because I only see some of their pictures. And if it's just their picture, I won't see the hand raised on everybody.
Okay. What she said.
Okay. All right, so we are now that you've gotten a chance to explore it, I hope you looked at lots of different ones. Does anybody want to raise their hand and offer which is the first solution I should implement?
Tamara, I'm not seeing a raise hand option in the participant list. I know I've seen it before, but I don't see it.
Let's see. Yeah, you're right. I don't see it either. Okay, never mind.
We could do it in the reactions. Oh,
Yes, maybe people can just.
Okay, Carlton, I see Carlton. Maybe your picture will come to the top. Oh, I see it. Nickel K also. So we'll start with Carlton.
Let's say increase renewables.
Okay.
It seems to be a pathway that we're already headed towards, so it's easier and most palatable right now, probably.
Okay, so we've let's increase, let's subsidize. Let's get that a little bit higher. I'm having trouble here getting this to move. There we go, subsidize. All right, let's see. So the green line went up significantly. Let's replay that. And you can see that oil, coal, and natural gas came down while renewables go up. But also notice when this actually occurred, when most of that actually occurs, almost nothing is impacted between 2020 and 2040. Most of it is between 2080 and 2100. And we've gotten it down from 3.5 to 3.6 to 3.5, or 6.5 Fahrenheit to 6.3 Fahrenheit. So Nickel K, I don't know your actual name. Do you want to offer a solution?
Okay, can you hear me now?
Yes.
Hi, it's Karen Nickel.
Oh, Karen Nickel.
Yes, and I just had a question because I was going to go for the renewables as well. But my question was, does that include offering, when you say subsidize, offering subsidies to the population, or is it just to technology?
So what we can do is we can look under here, and this will be, so this is basically this subsidy is a you're subsidizing so that it's 2 cents per kilowatt hour less expensive. And what this is it's to the renewable energy producers. So it's not to the people that you are asking about.
And so is there a way, because I see one of the significant ways, if you get rid of that renewables tab there, one of the significant strategies was to increase your carbon price.
Okay.
But is there a way to offer any kind of subsidy for electric usage or for renewable usage by the population? I'm thinking to impact the.
Well, that was, so the way you should think about that is this: if there's a carbon price, the question is the price of carbon, the money comes in, and then what does that do? What you have to do is say that you need to implement a plan to distribute that money to those who are in need, low income families, so that they can afford energy. So that was the way that I would address how to redistribute the money that comes in from a carbon price or a coal price or an oil price or a natural gas price.
Okay.
Okay.
Thank you.
Catherine?
I had good luck with the carbon removal technology. And
Okay.
pushing that all the way up.
Well, let's just do it in increments now. So we got down from 3.5 to 3.3 degrees Celsius. And so this is medium growth of that technology. If we do go the full distance, that gets us down to 3.0. And let's see what it says under here. So this actually says, what are the sources of, so these are the different types of technologies that bring that, that take that carbon out of the air. So there's afforestation, this is carbon capture and storage, biochar, agricultural soil carbon. These are in that Google Doc, in the Google folder. There is one page document that talks about this net removals and talks about each of these. So this is direct air capture and mineralization. And so when we did the maximum potential, that was 100% here. And so you can also increase, you can identify these individually and say that you're increasing them individually, and to see which ones are the most impactful in terms of each of these different kinds of technologies to remove carbon. Okay, so we've gotten now down to 3.0. So let's see, Ashley. If I've already answered yours, could you put your hand down so that, or remove your little symbol, because I don't know that I'll see everybody else. Ashley?
What about increasing the energy efficiency in either transportation or buildings and industry?
All right, let's try buildings and industry first. I'm interested to see. So that got us down to 2.8. I highly increased it. And what does that actually mean? If we go here, it means you're increasing the energy efficiency by 3% per year is what that means. And if you replay this change, you can see that it doesn't have, wait, what happened? Didn't go, there we go. So all of these go down. And the reason is that by increasing energy efficiency, you're having a less of a demand on efficiency. So what I'm going to do now is see how I'm going to put this back here, and I'm just going to increase energy of transportation. This has to be right on 0. There we go, to 3.0. Now I'm going to increase this one to highly increase. You see, this one didn't get us as far, and let's see what percentage that is. That's only 2%, 2.7% less. So let's make it the same as we had for the energy, and you see that it's still not. We got, what did we get down? We got down to 3.0. This gets us to 2.9. So increasing the energy efficiency of transportation by the same percentage gets us a little bit further than in buildings and industry. But now I'm going to add them together and see what happens. And that got us to 2.6. So let's see. I'm going to go back and put these both at 0. And so that was 3.0 to 2.8. Oh, energy efficiency in buildings and industry is a little bit more impactful. It went from 3.0 to 2.8. So that's 0.2 degrees Celsius. And the other one was from 3.0 to 2.9, which is 0.2. So together they would be 0.5, but it didn't, wait, this one I had to change even further. I had to change this to 3. I'm just trying to make the change the same. So that gets us down to 2.7 here. So it only, the total got to be a total impact of 0.3 degrees C, whereas individually, this one was 0.2 and this one was 0.3. So you can see that they're not additive in this case. Okay, does anybody else have some suggestions? Other suggestions? No other suggestions? Ashley?
What if you taxed coal just a little bit or oil just a little bit?
Okay, so that got us down to 2.6. And I'm just going to add them up here because we're running out of time, but I'm going to tax. Oh, but one of the things that I would suggest, instead of impacting them, taxing them individually, if you tax carbon, basically you're impacting coal, oil, and gas. You're adding a tax to all three because the carbon price is dependent on the intensity of carbon, and coal is the most carbon intensive, oil is the next most carbon intensive, and natural gas is a third, but they all have carbon in it. So when I implemented the carbon tax and hit replay, you can see that all of those, the red, brown, and blue lines went down and the renewable energy went up, and that got us down to 2.1. So we're getting close. And one other one that I'll suggest, because this is kind of interesting too, this is methane and other gases, and you can make those changes separately for agriculture and waste emissions versus energy and industrial emissions. So if you're talking about a vegetarian diet, so less meat production, you can decrease these. And so if I decrease it there, so now we've gotten down to 2.0. So we've kind of reached that goal. I haven't gone through all of the equity considerations, but one of the things that I wanted to get to here was to help you think about how you might, I'm going to go to this last graph here, this last slide. So this gives you a sense of what you can do. One of the things about the En-ROADS model, all of these solutions are making the assumption that they're being implemented worldwide. We know that that's not practical. There are some locations in which some solutions are much more effective than other solutions. But if the model has been set up so that you think about what's going to happen, what will happen if the entire world does it. And that's what this slide kind of gets at, is what people can do at a personal level. Each of your individual actions by themselves won't have a large impact. But if you can then influence your families and your students and your communities, then it will reach out and become a larger social movement, impacting organizations and the public, and ultimately changing cultural norms. And by trying to implement, in getting to this level, you really have to take into account more than just the impact of the science of the climate system. You really have to think about the social and economic impacts. And so what I wanted to point you to was these student assignments. I've actually did end up using these in my class. Yeah, I put they're in, this is a different location. This is a different Google folder, but I have the 4 student assignments, exactly this, in the folder for this workshop. So you can find them there. And I've used the short student assignment. Let's just open one of these. Basically what the assignment is so that there's a number of ways you can, in Climate Interactive, the organization that built the model, has a training program to teach you how to use the model and runs these kinds of workshops. And I've actually been through that, and I've run on the order of 35 workshops in the past year. But this is the assignment, and I actually implemented this in my class. I was going to run a workshop, but for something that happened in my personal life, I became a grandmother, which was exciting, but it impacted my class, being able to teach my class. So instead of running the workshop, I gave them this assignment. You can have them look at a 20-minute video of how the model actually works. So the demonstration that I did, it's a little bit more formalized there. They have them develop a scenario where, unlike what I told you, is not to get to 2 degrees C by yourself. In this case, they develop a scenario of a suite of solutions that gets them to 2 degrees C. And then they have to answer these questions. So the first one is about the actual plan. But then looking at the other aspects of it, what is the political feasibility of this plan? Who are the winners and losers? That gets at those equity issues. What were the surprises? What was surprising to you, especially that with that systems dynamic aspect? The model can reveal to your students things that they would not be able to see on their own. And then what are the trends the world can give you for hope that your solution is possible, and then what personal actions they might take. And so this is a short student assignment. There is the longer one, which I won't go over now, but is there available to you. That's more like a sort of a multiple week kind of activity that it involves your students digging in much more. So I was going to end there. If you're interested in the potential training, Climate Interactive, their website, you can actually go to that. I think I have that here. Let's see. So this is the website, and so that's the line to the model. The simulator is right here, the link. Then the tools for use, but then you can go to the work to all the slides. I've adapted the slides, but the slides are available for free from Climate Interactive. Here is the student assignments that you can do. And then this is the ambassadors program. And there's actually an online training that's going on right now for climate ambassadors. The other piece that may be of interest is this is the implementations of En-ROADS around the world. So the model was released in December of 2019, and there have been almost 2,500 events like this, reaching over almost 63,000 participants around the world. So it's truly an international effort. And so with that, I will end. Let's see if I have my last slide here. There we go.
Thank you, Tamara.
Okay.
Thank you very much. Was that that last link that you showed us to where they could get more training? Is that climateinteractive.org?
Well, you can get there from there. The more direct one, I'll put it in the chat, is enroads.org.
I
That
just
would
put
be
it
great.
in there actually, but feel free to do it again.
Okay. Yeah, no, that
Thanks,
site that
Caitlin.
I went to is En-ROADS. It's where the model is and where all the resources, it's very transparent. There is a guide that gives you all of the equations that were used. Another thing that may be of interest let me try to get rid of this, is I lost my train of thought. Sorry. Oh, yes, in the simulations, you can go to assumptions. This tells you for each assumption, and you can change them. So if you don't agree with them, you can change the sensitivity of each of these components of the Earth system and see what the impact that has. Another thing that you can do, which is, I've not really done this, you can look at the impact on GDP, so basically on the economy. You can look at those kinds of impacts also compared to economic models that various academics have published. So that's another avenue, but let me see, I was going to put in the chat. So Climate Interactive, the climateinteractive.org will get you to the site that gets you to both. There's another model called C-ROADS, the Climate Rapid Overview and Decision Support Model. I've also used that in my class. That is a simulation of a UN negotiation for the Paris Agreement. So it's a different kind of model, but both of those are available on the climateinteractive.org site.
That's fantastic. So much to dig through, and I'll remind everybody that all these things are linked on your roadmap. And it is time for another short break for stretching and other biological needs. We will come back here at 4:25